Quantum computing, it's not just the future, it's the next revolution in how we think about information itself. Unlike classical computers that use bits, simple zeros and ones, quantum computers use qubits, which can be both 0 and 1 at the same time, thanks to the weird and wonderful laws of quantum mechanics. This means quantum computers can process enormous amounts of data in parallel, solving problems that would take today's supercomputers thousands of years. But here's where it gets really interesting. Not all quantum computers are built the same way. In fact, scientists and tech companies around the world are experimenting with completely different ways to create and control qubits. Let's take a look at some of the leading approaches shaping the future of computing. First up, superconducting qubits. This is the approach used by big names like IBM and Google. These systems use tiny electrical circuits made from superconducting materials, cooled down to near absolute zero. The extreme cold removes resistance, allowing quantum effects to flourish. It's fast and proven, but keeping it that cold is a huge challenge. Next, trapped ion quantum computers. Companies like IonQ and Quantinuum trap individual atoms using electromagnetic fields and control them with lasers. Each atom becomes a qubit. This method offers incredible precision and stability, but it's harder to scale to large numbers of qubits. Then there are photonic quantum computers. These use light, literally particles of photons, to carry and process quantum information. They can operate at room temperature and transmit data at the speed of light. Companies like Xanadu and PsiQuantum are betting big on this approach, hoping it will be easier to scale up using existing optical technology. Another exciting area is topological qubits. This one's still experimental, but potentially game-changing. It's based on creating qubits that are naturally protected from errors due to the way their quantum states are arranged in space. If successful, it could solve one of quantum computing's biggest problems, noise and instability. And finally, neutral atom qubits. Here, scientists arrange neutral atoms into 3D grids using lasers, letting them interact to perform quantum operations. It's one of the newest and most flexible designs, showing real promise for large, scalable systems. Each of these technologies has strengths and weaknesses. Some are fast, some are stable, and some are easier to scale. But they all share one goal: to harness the power of quantum mechanics to do what classical computers simply can't. Quantum computing isn't just one technology. It's a universe of approaches, all racing toward the same dream. Cracking the code of quantum life. From superconductors to photons, from atoms to light itself. The question isn't if we'll reach true quantum advantage, but who will get there first. So, what do you think? Which quantum approach will win the race to the